Hi everyone, welcome back. This is part 2 of atoms, molecules, and ions. And in this portion, in sections 2.2, we're going to talk about the discovery of the electron, the proton, and the nucleus, and then look a little bit at the nuclear model of the atom, and then a little bit about the neutron. And so all of this came about because of a lot of experimentation and reporting and researching and sharing among scientists to come up with this. And so we're going to talk about some of this, but I'm not going to go into great detail like I said earlier. If you want to understand a lot of the things that went into these experiments, because they're like beautifully simple and yet very effective, feel free to look in the book for more information or Google it, right? Okay, so in the early 1850s, okay, there were a lot of scientists that were looking at the particles. They were trying to decide, is matter made up of particles or waves like light, or what exactly is going on? And so all of this led to the discovery of electrons, protons, and neutrons in the late 1800s. And so there was a gentleman by the name of J.J. Thomson, and he is the person who discovered electrons. So J.J. Thomson, electrons. That's what you need to remember as far as this goes, okay? And this was a great cathode ray tube is what this is known as, the cathode ray tube experiment. But basically, it allowed him to figure out that there were particles that were moving that were negatively charged, okay? And so the cathode was a negative and the anode is a positive, just like in a battery. And so the electrons were attracted to the positively charged, and repulsed by the negatively charged. And so that's how he figured this out. Now, like I said, you don't have to understand this whole experiment, but if you want to, there's some really interesting things. This is what a cathode ray tube looks like. Okay, and a cathode ray is attracted to the positive plate, so the negatively charged particles would show up as electrons. And so, but what you need to know is that J.J. Thomson discovered electrons. He also discovered something called a charged mass ratio, and this is something that we talk about more in Chem 2. But it uses coulombs, okay? But again, you're not going to have to do any calculations or anything, or really understand a whole lot about the charge to mass ratios. The important part is that he used this charge to mass ratio to then let Millikan, who used something called an oil drop experiment, to determine the charge of the electron. And basically what happened was that he decided, he came up mathematically and with experimental data, that the charge of an electron was a negative 1.6022 times 10 to the minus 19 coulombs, and the charge to mass ratio of the electron from Thomson's experiment, he said that the charge to mass ratio was 1.76 coulomb times 10 to the 8th coulombs per gram of electrons. And so when you put that in there, you can actually cancel out, like we saw earlier, and you can figure out what the mass is of the electron. And so by using those two numbers from those two experiments, we came up with 9.10 times 10 to the minus 28 grams. That's really, really small, okay? So that's why we're going to see later that we don't even use electrons when we're calculating the mass of an atom or an element. Rutherford is the next guy we're going to talk about, okay? Rutherford's experiment said that atoms contain negatively charged electrons, but the atom is neutral overall. Okay, and so he used this gold foil experiment. Okay, so Rutherford used the gold foil experiment, and he noticed that when you were bombarding this with alpha particles, or bombarding it, sorry, with the electrons, the alpha particles were being emitted, and you would emit those, and they would be I'm trying to find my pen here, go towards this gold foil. Now, some things went all the way through, and some things were deflected. Okay, and so we're looking at basically the element of gold as this is happening. And so what he was able to figure out was that the atom's positive charges were all concentrated in the nucleus because a lot of those negative charges were being deflected. And so the positively charged particles are now called protons, and protons were nearly 2,000 times the mass of an electron. But there was one problem. So Rutherford was figured out the nucleus had mostly positive charges in there, but it was overall neutral. Chadwick, though, kind of, and again, see, everybody's building on everybody else's research, which is how it should be in science. Chadwick established the existence of the third type of subatomic particle called the neutron. And the neutrons are electrically neutral, but they have a mass that's pretty close to a proton, okay? And so the mass ratio being a little off with some of the previous experiments was explained by this fact that you also, in addition to having positively charged protons, you also had neutral neutrons, but so the overall particle was positive in the nucleus and negative outside where the electrons were. So here are the just a summary of electrons, which have a very tiny mass compared to the protons and the neutrons, and you can see here protons and neutrons have basically the same. The electrons have this charge in coulombs that we saw earlier, and then the positive number of that with the same magnitude is the charge of the protons. So to simplify, we just say the -1 charge on the electron plus 1 charge on the proton and a 0 or neutral charge on the neutron. And since 10 to the -28 is a lot smaller than 10 to the -24, we say that electrons have negligible mass. I always say, like, it's like me standing on the scale and weighing and a fly landed on me. That's like the difference. Okay? All right. So that is how we found out the structure of the atom. And we are going to, in the next section, talk a little bit about, and so I'm gonna include part 3 in this, if I can get everything oriented right. Part 3 is going to cover, all right, it's making me mad. The atomic number, atomic mass number, and what isotopes are, okay? So you're going to see some letters. We're going to use some letters to designate these. All right, so first of all, the atomic number we call Z. That's the number of protons. So the number of an atom, okay, is the number of protons, and this is the actual identity of an element because The number of protons will always be the same. If it's not, it's a different element. So the atomic number is the identity of the element, and it is equal to the number of protons. The number of electrons are going to be equal to the number of protons in a neutral atom. Okay? So if you know the number of protons, you know the number of electrons. The mass number, which is the last little bit of information here, is the total number of neutrons and protons. So you can take the mass number minus the atomic number, and that'll give you the number of neutrons. All right, and I'm going to show you how we use that here in the next couple of slides. So you're going to see these elements written in this form, where you're going to have A, which is your atomic mass, written up top, and then Z, the atomic number or number of protons, and then the symbol X here. Okay, so for example, if I have carbon, the mass of carbon is 12, the number of carbon is 6. Okay, and then the C stands for carbon. If I want to know how many neutrons, all I have to do is say 12 minus 6 is 6. Because this is protons plus neutrons, and this is protons, and so the difference is how many neutrons there are. Most elements we're going to see have more than one form that occurs in nature, and so we say they have 2 or more isotopes. Isotopes have the same atomic number, that is the same number of protons, but a different mass number or different number of neutrons. So if we look at uranium here as an example, uranium comes in mostly two forms. It comes in uranium-235 or uranium-238. And we can also write this as U-235 or U-238. Why? Because they're both going to have 92 protons or 92 mass number. But remember how we had these written so that the mass is on top and the number is on the bottom. So when I subtract those two numbers, I can find out how many neutrons there are. Notice that there are 143 neutrons in U-235, but there are 146 in U-238. So the only difference between these two isotopes is how many neutrons there are. So I got this one for you, and I've got it typed out because it was a little bit easier to get all these Z's and all that stuff. But for A, we have chlorine 35. 17 is its number, and if you look on the the periodic table of elements, you're going to see that it's number 17. And so that means that Z is 17. So there are 17 protons. And A is 35. So the number of neutrons and protons is 35. So to find the number of neutrons, we say 35 minus 17 is 18. And that tells us there are 18 neutrons. And since protons and electrons are equal, we also know that it must have 17 electrons. In chlorine 37, it still has 17 protons because it has to, which means it also has 17 electrons. But we can calculate that it actually has 20 neutrons, because 37 minus 17 is 20. So those are isotopes because they have the same number of protons, but they have different masses or different numbers of neutrons. Now this next one, I just have potassium 41. Potassium 41 because if you look on the periodic table, you can find its number from its symbol. The symbol for potassium is K. It's a weirdo. And so you can find the 19 goes with K. So that is its atomic number. Okay, so that's its atomic number. So there are 19 protons and 19 electrons, and then 41 minus 19, which is 22 neutrons. All right, and then I showed you carbon 12, and this is carbon 14. So carbon 14, if we wrote it with its symbol, would be like that, okay? And so I can already figure out I've got 6 protons, 6 electrons, and then 14 minus 6 are 8 neutrons. So see how that works? Not too hard, right? So I'm giving you a practice one to work on this so that you can go through. This time what I'm wanting you to do is give that symbol by seeing how many protons and neutrons and electrons you have. So you're going backwards from the way I just did it in your practice problem. All right, so thanks for staying with me, and I will see you for part 4.